All right. Today we're going to talk about Bernoulli's and Bernoulli's equation. We'll talk about its assumptions. We'll apply it to a tank of water and then kind of show you how you can also write it a different way. All right. So when you hear Bernoulli's, we're going to start with that. We're going to just pretend or think about it as a conservation of energy. Like in physics, if you have a ball and you drop it from a certain height, you have potential, and then that converts it to kinetic, right? Or if you're, say, you're pulling back a pinball machine, getting ready to shoot it out, you have potential in that spring, converts it to kinetic. Or if you're shooting a bow. Well, in fluid mechanics, when you're dealing with fluids, which is a gas or a liquid, that also has its energy. Okay. You could have kinetic, you can have potential, and you can also have what they call pressure energy. Okay. So for example, you might have done this before where you have your garden hose, you stick your thumb on the ends, the diameter gets smaller, shoots up. You can use the Bernoulli's equation to figure out from state 1 to state 2 to find your maximum height using Bernoulli's. Okay. Here's a squirt gun. Usually squirt guns are pressurized, right? You can pump it up. Okay, so you have a certain pressure inside at state 1. You hit the trigger, and then it shoots out, and it converts it to velocity or kinetic. Okay. Over here, usually airplanes have what they call a pedostatic tube, and we can use Bernoulli's between this point and this point. We can find a delta P, and we can use the Bernoulli's equation to figure out the velocity that airplane is moving at. Okay. Also, you can use Bernoulli's, or Bernoulli's is kind of in effect. For example, in an RC boat, you see this spot right here where this is like a tube. It's cut at an angle. Okay, that creates a high pressure and shoots out the water, okay, on the side of the boat. All right, so you're using pressure differences to get flow through something. Okay, very similar process when you're dealing with like a paint sprayer. Okay, it creates this suction, and you can use Bernoulli's to figure out the velocity. Okay, so again, we're dealing with fluids, which is liquid or a gas, and they have their own energy. Okay, and when we're dealing with Bernoulli's and energy, we're only focusing on, like, there's no temperature differences, there's no friction, it's steady flow. There is no like input of power, like shaft work. Okay, we're talking incompressible flow and no heat transfer. Okay, so this is the equation. So let's write it down. Bernoulli's. We have P1 over rho plus V1 squared over 2 plus GZ1 equals P2 over rho plus V2 squared over 2 plus GZ2. So when we're dealing with Bernoulli's, we're going from one state to the next state. So state 1 to 2. And you notice a lot of these have state 1 and state 2. So what does that mean? That means that this number, C1, a constant, will equal this number over here. Okay? I'm just going to erase those. So each one of these terms, this is what we call pressure energy. This is your kinetic energy. Oh. And this is your potential energy. Okay. Again, this is conservation of energy for a fluid, and the assumptions are steady flow, no friction, which pretty much is no heat transfer, no shaft work, so no input in power or anything. We're not inputting power in anything, okay? So it's an assumption, it's an ideal case, and it's used pretty frequently to figure out something in terms of velocity or your pressure changes, to give you an idea of the ballpark. Okay, again, steady flow, no friction, no heat transfer, no shaft or no input power. Okay, we're not adding a pump or subtracting a turbine or including losses such as pipes or elbows. Okay, we will get to there. It's called modified Bernoulli's, where we can add a pump, we can take away a turbine, and we're going to add or subtract minor losses. Okay. So we have the equation and we have the assumptions. And again, this is the energy of the fluid. Okay, so in this squirt gun, it's just the energy of the liquid water. Okay, and we'll leave it at that. Because in thermodynamics, what you do is this part is part of a bigger conservation of energy for a particular system. Okay. So this is just looking at the fluid part only. In this pitot tube, you're only looking at the flow of the air. And I'll have a video on pitot tube and how do we derive the equation on that. Okay. Now, let's go through and look at two things. I'm going to show you first if the fluid was at rest. Okay. So that means V1 equals V2, and that's 0. So I'm going to rewrite the equation, P1 over rho plus V1 squared over 2 plus GZ1 equals P2 over rho plus V2 squared over 2 plus GZ2. Hopefully I did a 2, yes. So if it's at rest, that means that term is gone, that term is gone. Okay. So we end up getting, after a while, P2 minus P1 equals rho GH, which we can say P2 equals P1 plus rho GH. That should look familiar. That is your hydrostatic or force equation or pressure equation as a function of height. So we can use Bernoulli's and actually kind of derive that pressure with height equation. Okay. Pretty cool. Okay. Let's look at, I'm going to scroll over here. Torsel's law. Torsel's law. I think I'm saying it right. Which is pretty much like we're looking at a tank full of water. Okay. So here is a tank. We have water at it. And we're going to assume this is 0.1. And then it shoots out, and this is 0.2. Okay. We need to label a datum, which is a reference line. And we're going to call this Z1. So Z2 would be 0. So if we write the Bernoulli's, again, you're going to write this a lot. P2 over rho plus V2 squared over 2 plus GZ2. we can cancel a few things. We're going to assume that the velocity at 1 is 0 compared to the velocity at 2. Okay, because it's a big tank compared to that small diameter outlet. That velocity is much smaller. We're also going to assume gauge pressure. So P1 is to atmosphere, which we have this symbol, right? So the gauge of atmosphere is 0, so that goes away. Okay. Also, 0.2 shoots out to atmosphere, so that's gone away. All right, and we said that Z2 is 0. So we have V2 squared over 2 equals G. So, oh, I forgot one. I wrote it wrong. It's like, where did the Z go? Z1. Yep, there we go. So GZ1. Hopefully you caught that. So V2 is the square root of 2GZ. Okay, or sometimes you've heard it as 2GH. So the velocity coming out of this, say, pool, say you popped a hole in it, in the pool, you can quickly get an estimate of the velocity coming out of that by taking the square root of 2g times the height that hole is popped at. Okay, this gives you a rough idea and kind of how we use Bernoulli's in conservation of energy. All right, so this is Bernoulli's. Bernoulli's, again, is conservation of energy of a fluid only, where we have steady flow, no friction, no heat transfer, and there is no mechanical work, no shaft. There's nothing in here that's spinning the pool, right? There's not a shaft or a pump, okay? And if you notice, I'm always going the direction that the flow goes. So it actually will go from 1 to 2. So you have to write it that way. That's how you do 0.1 to 2, okay? It's always the direction. And the energy a fluid has is kinetic, potential, but it also has this pressure energy because you can pressurize it. For example, like if you have an air compressor tank, you pressurize that tank. When you open it up, it shoots right out, right? So, and this is part of a small part in a bigger conservation of energy when you get to thermal, okay? Because if you think about it, this squirt gun could actually be moving in space along with shooting the liquid, all right? So you got to factor all of that in, okay? All right, this is Bernoulli's, and the next video will be on a pitot-static tube and how we get the equation to calculate speed. All right, the last thing I want to talk about are other ways we can write the Bernoulli's equation. Other forms of Bernoulli's equation. So I'm just going to rewrite what I've been writing. Which is P1 over rho plus V1 squared over 2 plus GZ equals P2 over rho plus V2 squared over 2 plus GZ2. Each one of these has a unit of energy or joule. Okay. We could also multiply everything by rho. So P1 plus rho V1 squared over 2 plus rho GZ equals P2 plus rho V2 squared over 2 plus rho GZ2. And hopefully you could see this. This is now pressure. Pascals. We could also divide, using the first term of the energy, divide each term by G. So P1 over rho G plus V1 squared over 2G plus Z1 equals P2 over rho G plus V2 squared over 2G plus Z2. This is like what we call, this is definition of like pressure head, velocity head, elevation head, okay? So these are all basically what we call head values, and they're meters or feet, okay? We're going to pretty much use this one when we start doing stuff with losses, pumps, and stuff, okay? All right, so these are other ways that you can write. It doesn't matter which way you use it. Pick one and remember it, and then go from there. All right. Thank you. If you have questions, let me know.